Lead-acid versus lithium-ion batteries. Over recent years, lithium-ion batteries have surged in popularity and overtaken lead-acid batteries as the preferred option for solar storage systems. Lead-acid battery technology is still advancing, with the release of high-performance tubular gel batteries as well as advanced lead-carbon batteries. In this video, we will look at the different batteries and compare the popular lithium-ion (LFP) batteries against the latest deep-cycle lead-acid and lead-carbon batteries. A direct comparison is not easy as each battery model behaves differently depending on the rate of discharge, depth of discharge, and the cycle life of the battery. Best battery type for solar storage. Lithium-ion batteries are now widely regarded as the best battery type for general energy storage, due to the high energy density and very high efficiency. There is, however, more than one type of lithium battery available. Most lithium batteries used for home energy storage generally use lithium iron phosphate, LiFePO4 or LFP, due to its lower cost and long cycle life. However, several well-known manufacturers such as Tesla and LG use lithium NMC cells. Battery capacity, depth of discharge. Battery capacity is measured in either amp hours or kilowatt hours, and the amount of capacity that can be used is known as the depth of discharge or DOD, and is taken as a percentage of total battery capacity. To convert amp hours to kilowatt hours, simply multiply the battery amp hour rating by the total battery bank voltage. As a general guide, lithium batteries are designed to be discharged up to 90% total capacity, while the traditional lead-acid batteries are generally not discharged more than 30 to 40% on a daily basis, as that would damage the battery. Battery usable capacity. This table provides a guide on the maximum depth of discharge for different batteries. It should, however, be noted that manufacturer's specifications should always be followed, as battery warranty may be void if deep discharge occurs lower than what is specified for the specific battery. Advanced tubular gel and lead-carbon batteries are more durable than traditional gel and AGM batteries and can sustain much greater depth of discharge, with up to 70% available. However, battery cycle life will be severely reduced if deep discharges occur on a daily basis. Unsealed or flooded lead-acid batteries is not considered viable options, as they require high levels of maintenance and any cost savings will be outweighed by maintenance work required throughout the life of the battery. Lithium batteries have many advantages over traditional lead-acid, especially with regards to usable capacity, weight, storage space and life cycle performance. Advantages of lead-acid batteries. Lead-acid battery technology has been around for over 100 years, so it's a very well-proven technology as well as being very safe and reliable when sized and installed correctly. For larger off-grid systems, lead-acid batteries are still one of the most trusted options, and a correctly designed system can typically last 10 to 15 years or even longer. Unlike lithium batteries, lead-acid battery banks do not have a specific cutoff point at a certain depth of discharge, so in an emergency situation they can continue to provide power until the voltage reaches the inverter cutoff. However, this is not recommended, as it will significantly reduce battery life. Deep cycle lead-acid batteries have been around for decades, but more recently advanced, tubular, gel deep cycle batteries have taken lead-acid further with up to a 15-year lifespan. There are many well-established companies producing very high-quality tubular gel lead-acid and lead-carbon batteries. Advantages of lithium batteries. The most obvious advantage of lithium batteries is the compact size and weight due to the extremely high energy density. Generally speaking, a lithium battery is about 25% of the size and weight of an equivalent lead-acid battery, which is helped by the much higher depth of discharge available in a lithium battery. Lithium battery systems are generally made up of smaller, easy-to-handle modules with sizes ranging from 2 to 20 kilowatt-hours, which provides a lot more flexibility when sizing a battery system. This also enables additional capacity to be added if needed at a later stage. When under load, the voltage drop of lithium is also very low and will not generally fluctuate more than 1 to 2 volts from nominal loads. This is due to the much lower internal resistance compared to lead-acid batteries. The low resistance leads to the greatest advantage of lithium, which is the low losses during charging and discharging, resulting in very high efficiency. Battery efficiency. Battery efficiency is the charging and discharging efficiency or losses during use. Due to the laws of physics, the transfer of energy from one form to another results in energy loss. In this case, the transfer is from electrical to chemical energy during battery charging, and chemical back to electrical during discharge. Generally, losses from lead-acid batteries are much higher at 15 to 20%, while most lithium-ion batteries are significantly lower losses at between 2 to 8%. Another problem with lead-acid or lead-carbon battery systems is the much longer charge time compared to lithium systems. A lead-acid charge cycle can take 2 to 4 hours, depending on the depth of discharge. This means that during bad or intermittent weather the charge efficiency can be very low and a full charge may not be achieved, which can reduce battery life. In contrast, lithium batteries can charge very quickly, 1 to 2 hours, and can efficiently absorb energy at much higher rates. Also, unlike lead-acid batteries, lithium-ion batteries can tolerate partial state of charge for long periods of time without degradation or sulfation issues. Incomplete charging of lead-acid batteries on a regular basis can significantly reduce the life of most lead-acid batteries. Space and weight differences. Weight isn't always a big issue for many stationary installations, but if space is limited, then lead-acid batteries are problematic as they take up a considerable amount of space, plus require good ventilation and airflow to allow any gases to escape during charging, and to keep the batteries cool in higher temperatures. On the other hand, lithium batteries have a much higher energy density and thus require much less space. Another advantage is that lithium battery modules do not vent any dangerous gases during charging, and do not require the same amount of ventilation. This means they can generally be installed in most non-habitable rooms or garages without any concerns. Also, most lithium batteries have an internal battery monitoring system, BMS, which monitors cell temperature and voltages, and can shut down the battery if the temperature exceeds an upper limit, typically above 45 degrees Celsius. The BMS protection is a great safety feature, but lithium batteries should still not be installed in confined spaces or outside in hot, semi-exposed locations with no ventilation. Batteries for off-grid systems. More recently, lithium battery systems have become extremely popular for off-grid installations due to the high efficiency ranging between 95 to 98%. They also offer scalability, which in contrast to lead-acid battery banks, which have a fixed size or capacity and extra capacity cannot be added once installed. Possibly the biggest advantage with lithium when used off-grid is the ability to sustain a low state of charge for a prolonged period of time, without any negative effects such as sulfation, which is a common problem with lead-acid batteries. Thank you for watching this video. Please like and subscribe to this channel for more technology information.